Okay, so they give us y equals 4x. So it's a straight line, intercept at 0, slope of 4, probably steeper than that, but it's just a rough sketch. X equals 0, so that's this vertical line, the y-axis, and y equals 4 means it's this area. So this is the area, two-dimensional area that they're asked to rotate. We're rotating around the x-axis. Oops, so the rotation's happening this way. So what we want to do is find a formula for an infinitesimally small. Okay, so I guess this section's about using the washer method. Yeah, we want to be able to find out the volume of a washer. So a washer is just like a right cylinder, except there's a hole in the center of it. Here's my right cylinder. And then there's a hole in the center of it, so we got to subtract out the area of the hole. So to do that, we should find a function that tells us the area of the inner hole and subtract that from the area of this total area, this total place. It's bad language. Let me try that again. We should find a formula for the volume of this area here, because it's constantly changing. You know, if you were to think about this figure being rotated, what's the volume of this part of the figure that's being rotated around the x-axis? And then you can find the volume of the whole thing that's being rotated around the x-axis and subtract the two. So you're thinking about right cylinders when you do that. So finding a volume of a right cylinder, it's always the same thing. It's pi r squared times h. But the height is changing with one of those. I don't think it's changing with the other. Look, the big cylinder, this big slice, if you were to picture a right cylinder being drawn through the entire area that we're revolving it around, this one's got some thickness to it. They're supposed to be infinitesimally small. But there's my really small right cylinder. That height is, let's see, the radius, I should say, is never changing in that cylinder. Okay, the radius for the bigger cylinder is always going to be 4, because that's the distance from 0 to y equals 4. So we've got this big cylinder, pi r squared times h, where h is, let's see, I'm going to integrate this with respect to x. Because x at the height is infinitesimally small. We're taking these really, really small cylinders. That's the big one, and we want to subtract that by the smaller one. Now, the smaller one's radius does change. So we've revolved this around the x-axis. This area constantly changes, right? So we need to define the radius with a function. And this is always dependent on y. We're going to put 4, I mean, it always equals the y value on this line, so we need to write it as 4x, because the radius depends on where you are. If you're at x equals 2, can we do that? That wouldn't be right. I confused myself because my drawing was bad. I was like, hey, what if x equals 2? But that's not possible, because if x equals 2, then we're not talking about the region. X equals 2 would give us y equals 8 for this line. So like if x equals 0.1, if you plug that into this equation, that spits out the height of, the radius of that cylinder, I should say. We're talking about these small right cylinders that we're drawing. Be dotted. Right, those are the volumes that we're calculating. The y values are the radius of the cylinder, so we need to plug in 4x in here, because you plug in a value for x and that spits out the y value, the radius. So this represents the radius of that smaller cylinder. And then we square that, and then we multiply by the height. And remember, that's the calculus part. The height is infinitely small. So in other words, if you plug it into that formula, we want to integrate from 0 to 1, and I'll show you why it's 1 in just a second. that's going to tell us the volume of the area as we rotate around the x-axis. Now it's 1 for the limits of integration, because if you find out where this crossing point is, this crossing point happens when the line y equals 4x meets up with the line y equals 4. If you solve that as a system of equations, x equals 1. So the crossing point is at x equals 1, which is the variable we're integrating. So if we just do the calculus part now, this is 16 pi minus 4x squared, so that's 16 pi x squared. I think I got that right, yep. And then if we take each antiderivative, this is 16 pi x, because that's just a constant. And then this is 3 is going to be bottom. This is 16 over 3 pi x to the third for an antiderivative. Evaluate that between 0 and 1. We can forget the 0 answer, because if you plug in 0, the whole thing becomes 0. So we got 16 pi minus 16 over 3 pi. So we get common denominators, 40. I know what that is, shouldn't I? Yeah, that is 48. 48 pi over 3 minus 16 pi over 3. 32 pi over 3 for a final answer.